pleasure to hand over to Dr. Fisher, who's going to give you a wonderful talk.
Thank you.
Thank you.
Thanks for having me. Well, thank you all for being here today. It's really terrific to be here and to be a small part of the CITRIS program. So the presentation that I'm going to give today is an overview of a larger project involving managed aquifer recharge, which, as you'll learn, is a technique for enhancing groundwater resources. And there's a component of this project that involves real-time monitoring with networks of environmental sensors, and that's the part for which CITRIS is largely responsible. My co-PI on the CITRIS seed grant that supported that part of the work is John Vasecki in electrical and computer engineering at UC Santa Cruz. And a number of the co-authors here are graduate students, 2 in Earth and Planetary Sciences, and Eric Castillo, who's been supported by the CITRIS seed funding as well. I'm also just going to start at the beginning to acknowledge a variety of other collaborators on the broader project, including a large number of students from the hydrogeology group at UCSC who have helped to collect copious amounts of field data. And without going through them all, I'll just thank all the funding sources who have supported different parts of this project over the last few years. So here's an overview. Knowing that the audience is not water resource, you guys are not all water resource experts, I want to take you through some of the background information that's helpful to provide context for the presentation and project. Talk about groundwater in California, and then move on to the Pajaro Valley Groundwater Basin, which is where this research is taking place in the central Monterey Bay area. Then we'll move on to the Harkin Slough project, which is the specific area of research. And I'm going to spend a little bit of time talking about using heat as a tracer for water flow. This being an engineering audience, I know you're not afraid of a few equations, and it's one of the few chances I get to sort of show how this method works with a crowd that I can expect can follow along. And then that explains where the CITRIS instrumentation fits in, because we developed the network of sensors in order to hopefully improve the use of heat as a tracer in groundwater infiltration. Then I'm going to wrap up by summarizing where I think the project is going. Indeed, this is CITRIS seed money. And we already have one larger proposal in with the National Science Foundation, and I'm meeting on Friday with the Resource Conservation District to talk about another project. And so we're quite hopeful that based on the results we found so far, we're going to be able to expand this work much more broadly, regionally, and indeed perhaps around the state. So first, a few concepts in groundwater. Groundwater, as many of you know, is water found below Earth's surface. It occupies pore spaces in rocks and underground formations. Some people picture groundwater as being an underground river. I know when I was little, when I first heard about groundwater, I imagined that there were sort of cataracts of whitewater rapids underneath the ground. And in my 5 or 6-year-old brain, I also imagined that there were sharks diving through the rapids in the underground rivers. And of course, there are no sharks. And in fact, there are very few underground rivers. Most of the groundwater is actually flowing through a tiny network of pore spaces, kind of like capillaries in your hand. An aquifer, then, is a geologic unit that can both store and transmit water. And this is important. You can have one of those two quantities or characteristics and not have a usable groundwater aquifer. And then a basin is a region that's underlain by aquifers, although often basins are defined on political or economic boundaries rather than on hydrologic boundaries. And that creates some challenges, including in the field area that we're going to look at in a minute. Now, when people talk about a groundwater basin, they often refer to something called the sustainable yield. And in a developed basin, this is the amount that you can pump over the long term without causing unacceptable harm. And that's not a hydrologic term. Unacceptable harm is somebody's definition. And it's one reason why determining the sustainable yield causes so much consternation. You hear other terms that are similar, basin yield or safe yield, but in essence they come back to the same thing. Now, this term is related to the total amount of recharge, that is water flowing into aquifers, but it's not the same. And I won't go into the details for that, but suffice it to say that in extracting water from the ground, we don't necessarily get to control where that water comes from. And that's the fundamental problem. So if the sustainable yield is exceeded in a basin for a long period of time, then this can lead to overdraft. And then overdraft is where unacceptable harm occurs. So you can define overdraft either by defining the yield, which as I've mentioned is tricky, or you can simply look for the effects of groundwater overdraft to decide that it's actually occurred. And in general, it's the latter approach that tends to work better. That is, you can get balled up arguing about what the sustainable yield is and never decide whether there is or isn't overdraft. But once you see the negative effects, you can be pretty confident. So here's the basis for this. In a groundwater basin, before it's developed, typically you have the basin in some kind of a dynamic equilibrium with whatever natural conditions exist. There are inputs of various kinds, there are outputs of various kinds, and when they find balance, then the amount of water stored in the aquifer is at some dynamic steady state. It doesn't mean there's no water going in or out, it just means that they balance. Typically what happens is when people get involved, something changes. Either inputs are reduced, outputs are increased, and as a result you get a change in the amount of water in storage. And it's when this occurs over the long term that an overdraft condition is determined to exist. And as a result of overdraft, there's a variety of negative impacts that can be felt. This is a classic picture from the San Joaquin Valley showing where the ground used to be in 1925, where it was in 1977. And that subsidence of the ground is caused by over-extraction of groundwater. Even more than the damage that's caused at the surface by subsidence, that represents a permanent loss of storage. And this is the real tragedy of overdraft, is that when groundwater pore spaces are eliminated by subsidence, or when they're intruded by seawater, then for all intents and purposes, they can be removed from being usable storage. So it can be a permanent loss. In the case of basins near the coast, and of course near the coast is where a lot of people live, the ocean can be brought in, and it only takes 1% seawater to make deionized water virtually unusable in terms of a groundwater supply. So it doesn't take a lot of seawater intrusion to cause a big, big problem. Now, one of the big challenges, of course, is that water in the hydrologic cycle is in motion. And of all the different fluxes in the hydrologic cycle, all the different parts that researchers have just spent person years studying, perhaps the most enigmatic and the most difficult to resolve of those fluxes involve groundwater. And that includes the rate of flow and especially the rate of recharge. One might argue that evapotranspiration, the return of soil water and surface water to the atmosphere, is an equal technical challenge. But there's been a lot of progress in the last 20 or 30 years in measuring ET, especially using satellite data sets. But groundwater tends to resist the application of that kind of technology because, in fact, the energy that's needed to get penetration of the ground just doesn't exist from satellites. So, in fact, virtually all measurements of things like recharge or water levels in storage in the ground require direct measurements. And this makes it both difficult and expensive and challenging. So I guess the point I want to make there is there's fundamental research to be done at a frontier in hydrology related to groundwater recharge. Now, in California, we lead the nation in many things, and that includes in our use of fresh water. This map is color-coded by water use. These are in millions of gallons per day. California uses more water than any place. Texas uses a lot, too, and a lot of that actually supports industries of various kinds, petroleum industry, chemical industry, and so forth. But we also lead the nation in the use of groundwater. And if you just wanted to average it out, about 50% of the freshwater supply in California is provided by groundwater. It's a little less during sort of normal to wet water years, but during dry years it's actually more. And that's because we don't stop farming or taking baths. Our industries don't shut down during droughts. Instead, we simply take the water where we can get the water, and that's typically out of the ground. Of course, the challenge in California with regard to water in general is that most of the rain falls in the northern part of the state, and most of the demand is in the central and the southern part of the state. And as a result, California has developed the largest, most intensive, most expensive, most amazing water supply and distribution system in the world. And these are the 10 major hydrologic regions defined by the Department of Water Resources. And the size of the arrows here shows the relative magnitudes of water transfers in the state of California. Now, what I want to point out is, in fact, the Central Coast hydrologic region, which goes roughly from Santa Cruz down to Santa Barbara, this is, in fact, essentially off the grid as far as statewide water transfer in California. In fact, this San Felipe transfer is less than what's shown here, or even non-existent. So the Central Coast region is kind of interesting in that sense. Now, where are we in the state in terms of groundwater use and water demand? When I arrived soon after I arrived in Santa Cruz, DWR put out their water plan update. This comes out every 5 years, give or take. And this was an assessment that was published in '98 indicating where the state stood with respect to water demand and water supply. And all of the numbers that are shown here are in units of millions of acre feet. An acre foot is just like it sounds. It's 200 feet by 200 feet. That's an acre, 1 foot deep. It's about enough water for 2 families for a year. Okay? So 1 million acre feet is enough water for 2 million families for a year. Okay? So these numbers show demand in the state, supply in the state, and then the difference between the two, supply and demand. Negative numbers mean that more water is being used than is available on a regular basis. Now we know that when the federal government runs a deficit, we can print money. Essentially, we sell bonds by printing money. But you can't print water. And you can't keep taking water out of rivers or reservoirs in excess of what flows in year after year after year to the tune of millions of acre feet. So a lot of this is groundwater overdraft. Okay? Not all of it, but a lot of it. And these are big numbers. What was shown in '95 was that the normal year deficit was 1.6 million acre feet. The dry year deficit was about 5 million acre feet. And the projection was that as of 2020, at a time when the population was going to go up by 50%, that these numbers would drop, that we would drive the normal year deficit almost to zero, and we would cut the dry year deficit in half. Okay, that was the prediction by the Department of Water Resources. So we're halfway there. From '95 to 2020, we're halfway there. We are living in the future. Okay? How are we doing? Not so well, it turns out. Here's the latest water plan update, the official version that was published in '05. And these numbers are somewhat larger in general because DWR included environmental uses of water in their budgeting. Now, the normal year deficit is gone up by a factor of 3 to 4. It's about 6 million acre feet. And the dry year deficit is 14 million acre feet. So we're halfway across the period of prediction, and things are much, much worse. The '09 water plan update hasn't officially been released, but I took a look at the draft, and it's virtually unchanged from these numbers that are shown here. Now, DWR doesn't define this as groundwater overdraft, but most of it has to be groundwater overdraft for the reasons I just described. You can't keep taking water out of rivers and reservoirs that doesn't exist. So what you need to do, therefore, is take more out of the ground than can be sustained. And the other thing that's interesting about the '05 water plan update is the first DWR update that even mentioned climate change. And none of the planning scenarios include climate change. So they mention that it probably is occurring, but they have no plan to deal with it as of '05. And of course, I won't get into it here, but I can answer questions after the talk if you like. There are going to be major impacts of climate change on the hydrologic cycle, and that will include impacts on both surface water supply and groundwater. Now, DWR recognizes there's a problem. They don't ignore that. And this is a plot showing where they estimate the new supplies of water are going to come from for the state of California. And these numbers are shown in millions of acre feet. Their number one new supply, quote unquote supply, is from urban conservation. And that's certainly an area where there have been great improvements. In fact, it's not well appreciated, but LA's population has gone up enormously in the past 20 years, and their total water use has remained essentially constant. And that's been achieved largely through reductions in per capita water use. But of course, as cities and regions save more and more water, you get conservation hardening. Your ability to conserve water gets reduced over time as people conserve more and more. The next highest predicted new supply of water is to come from enhanced groundwater storage. Okay, that's what DWR suggests. And then other sources can potentially take part as well. This plot shows the major hydrologic regions in California once again. The upper numbers indicate water use in millions of acre feet. It's from about 15 years ago. But the lower numbers are the percentages of freshwater supply that are provided by groundwater. And the Central Coast region, in addition to being virtually unconnected to the statewide water grid, uses a larger fraction of groundwater than any other part of the state. And in fact, this presents both challenges for this region and tremendous opportunities to make better use of enhanced groundwater storage. And in fact, the place we're going to be looking at is here in the northern part of that region on the central part of Monterey Bay, and that's an area known as the Pajaro Valley. So let's look at the Pajaro Valley in a little more detail. This purple area shows the Pajaro River watershed. It actually extends across 3,400 square kilometers and includes 4 counties in California. That water drains into Monterey Bay, which is shown here. And the Pajaro Valley groundwater basin is the area that's in orange. So the two basins don't correspond. There's a river basin, and then there's a groundwater basin. The primary water use in this area is for agriculture. It's one of the centers of high-value crops, things like strawberries and caneberries. It's also a center for high-value organic agriculture. Surface water systems in the Pajaro Valley are considered to be impaired by the US EPA, in many cases by multiple contaminants, things like sediment, nutrients, and pesticides. The primary freshwater source in this area is indeed groundwater. There's very little water being diverted from surface sources. It's virtually all pumped out of the ground. And over the long term, this is a basin in overdraft because the pumpage exceeds the sustainable yield. Looking here from the inland area towards the coast, here's a geologic cross-section through the basin. The primary aquifer in the coastal area is something known as the Aromas Formation. It's ancient dune sands and deposits left behind by rivers. It's a relatively thick sequence. It actually gets to several hundred feet as you get to the coast, but it pinches out as you work your way towards the back of the basin. There's another aquifer system underlying the basin that's used more extensively to the north, but it's not used as heavily in the Pajaro Valley. The area where we're doing our research overlies this Aromas aquifer system. Here's a blow-up of the area around the Pajaro Valley. Here's the Pajaro River. The city of Watsonville is the major population center, and the area around here then is the major ag center. Now the numbers of exactly how much water is used and exactly what the capacity of the basin is to satisfy demand, these numbers are subject to debate. And I'm not going to worry about trying to get them exactly right. Nobody knows what the exact truth is. But the pumping is on the order of 60 to 70,000 acre-feet per year. Of that, the city uses perhaps 10 to 13%. The sustainable yield of the basin is less than this. And we know that because water levels are dropping throughout the basin. And as a result, we have considerable overdraft. The overdraft could be as much as 60% of what's pumped on an annual basis. But as I say, these numbers are somewhat contentious. More than half the basin has groundwater levels below sea level. And as a result, because of the lowered groundwater levels, the ocean is moving in along the coast. This is a line that's crudely drawn. It generally indicates the demarcation of areas shown in red where the groundwater in the main aquifer has a salinity that's too high for many crops. When you get above 300, 400 parts per million total dissolved solids, then lettuce goes brown, strawberries don't produce big fruit, and other crops simply can't be grown. But the whole basin is actually suffering from the problem. These guys who are near the coast are the ones who see the effect of seawater intrusion because they happen to live next to the ocean. The folks in the back of the basin see water levels dropping. The places where you don't see water levels dropping are immediately adjacent to the major streams, which are some of the areas of primary recharge for the basin. But there's actually, you could give a whole talk on this. There's a long and ongoing political, economic, social fight going on in the basin to figure out exactly how this overdraft situation is going to be addressed. So there are a number of ways that one can look to improve groundwater conditions by increasing recharge. This can occur through areas of natural recharge or through managed recharge. And it's managed recharge that's the focus of this presentation. Within these systems, you can get water into the ground using wells or using surface impoundments. And this is the technique that I'll be talking about, which is surface recharge or managed aquifer recharge, primarily through the use of spreading basins. Here's a schematic that illustrates the concept. You have a surface water supply. Water is diverted from that supply. In the case of the Harkin Slough project, it's put into a shallow pond, and then it recharges into an underlying aquifer. In fact, this cartoon is from another part of the US, but this is essentially the situation in the Pajaro Valley at the Managed Recharge project on which we're working. There's a shallow clay layer which tends to allow some of that recharge water to pond, and then that water is later recovered by a well and distributed to local growers. So they have this water in lieu of the regional groundwater. Here's the field area. The Harkin Slough Managed Aquifer Recharge project is here. These are the Watsonville sloughs. It's quite a large wetland area. If you look at where the Harkin Slough project is located here, that area is blown up to the right, and there is a diagram of the recharge pond. It's about 300 meters by 100 meters, about 7.5 acres in area. Here's a map showing the main waterways for the Watsonville sloughs. There's a pump right here at the intersection of Watsonville Slough and Harkins Slough, and the water then is diverted and it's brought over into this pond. You can see it here in an image from Google Earth. And then here's what the pond looks like schematically. There's a number of monitoring wells that the Pajaro Valley Water Management Agency saw fit to install when the pond was in place. And in addition, there are a series of monitoring and testing points that we've installed as part of the research project. You're going to see a number of figures like this in the rest of the talk, and the figures just used to kind of orient you schematically on where you are in the pond. The water agency is permitted to divert up to 2,000 acre-feet of water per year when flows in Harkins Slough are high and when the water quality is good. That water would otherwise just flow out to the ocean. So this is mainly during the winter wet period when the flows are high enough and the water quality is good enough. Here's what that pond area looks like when it's dry. The pond is typically scraped out and it is sort of plowed or turned over a little bit to loosen up the soil. And then during the rainy season, when diversions occur, water gets moved into the pond and allowed to percolate into the underlying aquifer. This system's been operated for about 9 years now. It was put in place by the Pajaro Valley Water Management Agency, and we got involved starting in 2007 with trying to address a number of issues with pond operation, including getting more water into the ground and evaluating the impacts of managed recharge on the quality of that water. I'm not going to have a chance today to talk much about water quality, but if you have questions about it, I'm glad to answer those questions after the presentation's over. So we're looking at a whole variety of issues with this managed aquifer recharge system. One characteristic of these systems where they're used around California and around the world is they do tend to clog up over time. We're trying to understand why that's occurring here and what potentially could be done about it. We want to know how recharge varies around the pond to figure out if there are some parts that are more efficient than others. It's not enough just to monitor what's flowing in. You might want to know where in the pond you're actually getting the most benefit. We want to look at water quality issues, where the water goes, what effect it has on the groundwater resources. And then this is the place where the CITRIS work really comes into play, which is how projects like this can be linked and established throughout a region in order to achieve broader benefit, both in terms of getting more water into the ground, but also in terms of engaging a broader population. So this is a schematic. There's the pond area again, and this shows a variety of sites where we did a whole series of instrument installations, measurements, and sampling of various kinds. I'm not going to talk about all of these, but I'll just mention a couple. We have fluid samplers in this part of the pond, so we can collect water at different levels below the soil surface, find out what's happening to water quality during infiltration. We've got pressure and temperature gauges, which we use to estimate the rate of infiltration and the properties of the soil. And we also have collected hundreds of soil samples from multiple locations and depths to try to understand how the variations in grain size, spatially and temporally, may influence infiltration. So here's a couple of the results from the last few years of monitoring. First, we do a whole pond mass balance. This is to determine what the actual quantity of water is that's going into the ground. And the way we do this is we calculate the seepage or infiltration as a function of the rate of diversion, the rate of precipitation, subtract out evapotranspiration, that's water loss to the atmosphere, and then take into account changes in water level. In order to get this number correct, which is very important, we ran a LiDAR survey of the pond to create a high-resolution digital elevation model of the pond, which is shown here. And then based on that model, we can calculate for any given pond elevation down to a centimeter how much water is in storage at an instant in time. And by monitoring those changes in storage along with the other terms, we can calculate the rate of infiltration. And here's a result of when we do that. This is data from the 2008 water year. Water years run from the fall of the preceding year into the year of the number. So this is data from 07-08. We have data from 08-09 that we haven't quite finished processing yet, and we're out now collecting data from the 2010 water year. So this shows the stage in the pond. That's the elevation of the top of the pond. And you can see here that, in general, the stage goes up and the rate of infiltration goes up. These infiltration rates or seepage rates are normalized by the area of the bottom of the pond. So we take the total infiltration rate, divide by the wetted area, and this is the normalized rate. It's in meters per day. We get up to about a meter per day in a whole pond infiltration rate. This is very fast for groundwater, but not surprising. You fill up a pond like this water gets about 6 meters deep, and that drives the water into the ground. But interestingly, the stage stays high for several months. This is a period of about 6 months here. But after about 6 weeks, what we see is a decrease in the rate of infiltration. It levels off, it decreases some more, it levels off, even while the stage here is staying high. And here we're getting about 1/3 of the rate of peak infiltration, and here we're getting about 10% of the rate of peak infiltration. But remember, this is whole pond seepage. What we really want to know is what's going on place by place in the pond. So to get at this, we're applying a tool that's been used broadly, but a new technique. And this is using thermal measurements in order to determine seepage rates at a point. And I'm going to take you through how the method works. These are autonomous data loggers. They're a little bit shorter and a little bit fatter than this pointer. They're commercially available. They record temperature with a resolution of about 15 millik. And they can be suspended in a tube which is pounded into the bottom of the pond and backfilled with water, and they measure temperatures at multiple depths within the pond. Temperature oscillations in the pond itself, which are caused by diel cycles of daylight and nighttime, they propagate downward as thermal waves, and they are pushed downward by flowing water. So we've developed a method for analyzing the penetration of the thermal waves that allows us then to determine the seepage rate. And I'm going to take you through that method. So here's the concept. If you have a pond like this and a series of thermal sensors distributed with depth, the shallower sensors will give you the diurnal changes in temperature, the day-night cycles. As you go deeper below the surface, the peaks and troughs are attenuated, so the amplitudes are reduced, and they're also shifted in phase, so that the peaks and troughs are delayed the deeper you go into the ground. Our method is based on comparison of responses between pairs of sensors. So if you end up with n sensors, you can come up with 2 times n minus 1 pairs of different sensors against which you can apply this kind of a method. The one-dimensional advection dispersion equation for heat looks like this in the top. There's the advection part is here. This is the conduction part here. And wrapped up in conduction is the dispersion or spreading part of that equation. If you apply the appropriate boundary conditions to this equation with an oscillating temperature condition at the upper surface, then you get this solution. This has been published. It's not, the solution itself isn't a surprise, but it's kind of interesting. It's in 2 parts. There's an amplitude part and there's a phase part, and they're completely separate in the solution. And that means you can decouple them. We can analyze changes in amplitude independent from changes in phase and get a quasi-independent estimate of the infiltration rate on that basis. I'll just point out that the velocity that's in here is actually the velocity not of the water, but of the thermal front moving down through the base of the pond. And you have to convert that to the fluid velocity based on the storage capacity of the thermal storage capacity of the water in the soil. So if you break that equation into parts, you can solve for changes in amplitude, which is shown here, and you can solve for changes in phase, which is shown here. And what we did was take these equations and invert them to solve for the velocity of the thermal front. And we did so not in terms of the absolute depth of the sensors, but in terms of the difference in depth of pairs of sensors. And the reason this is important is in river systems or in ponds like this, the top surface of the soil is a moving boundary. And it moves because of erosion or the aggradation of material that gets added to the bottom of a stream or to the bottom of the pond. And you don't know a priori what the rate of motion of that boundary is. With this method, you don't care because it doesn't depend on the absolute depth of the sensors, only on the spacing between the sensors. It's independent of the motion of the boundary. So this was one of the key aspects of the new development that allows the method I'm going to show you to be applied. Here's what these equations look like. If you take this equation for velocity as a function of the ratio of amplitudes of 2 sensors, here's what that equation looks like. It's a nice monotonic equation which shows you the amplitude ratio as a function of the seepage rate and direction. So this is seepage up and this is seepage down. It works for flow in both directions through the bottom of a pond or a river, some feature like this. And essentially what happens is if you have rapid downward flow, you get no reduction in the amplitude of the thermal waves. And that's because the water carries the heat down so efficiently that essentially the thermal response at depth looks just like the thermal response at the surface. In contrast, when you have upward flow, then the thermal response at depth is attenuated. This is the derivative of that curve, and it illustrates where the peak response is. It's at low flow. And that's important because it means that you get nice resolution, high resolution under relatively low flow conditions. This is the phase shift response. This is the equation for the phase shift plotted up. And this is interesting because here you actually get the peak in the phase shift under conductive conditions. That's where there's no flow. And you get less phase shift out at higher flows. And in fact, in this case, there's symmetry in the response. You can't tell the difference between flow up or flow down in terms of phase shift. Fortunately, you can tell based on the amplitude reduction. So we can use the amplitude to get the direction, but the phase shift to get the flow rate at very high flow rates. So the sensitivity is high enough out at big flow rates that we can apply the phase shift here out at high rates when we can't apply the amplitude change. The reason that this works in the case of a river or a pond is because you have such strong diel signals. And this is a plot of the power spectrum for a surface water and then the power spectrum of a thermal probe deployed at about 20 centimeters depth below the bottom. In this case, a stream and a stream bed. And then this shows in the frequencies and their spectral response. Of course, you get the highest peak with the daily signal. And this isn't surprising. This day-night cycle puts a lot of heat into surface water for short periods of time, and it gives you the strongest signal. Here's some real data. Here's about 5 months of data from the Pajaro River. There's actually two curves plotted here, but you can't see them because of the scale. We filter that data to extract the diel signal. This is the filtered record. If you blow up just 3 days of that record, here's what it looks like. This is raw data on top, and then the filtered data on the bottom. And you can see these are for two probes, one at 10 centimeters depth and one at 20 centimeters depth. And you can see the attenuation of the amplitude, and you can see the shift in phase. Again, you get some of that just by conduction. It's the deviation from conduction that gives you the fluid flow rate. So to summarize, here's how the method works. You measure temperatures with inexpensive sensors, filter the data to extract the diel signal, calculate the amplitude ratio and the phase shift, and you can see how nicely these correlate with each other because they're both reflecting the same process. And then you use a program to then iterate and solve for the fluid flow rate. And here's 5 months of data showing daily seepage rates in the bottom of the Pajaro River in units of meters per day. I'm not going to go into a bunch of other details about the method, but to get from here to here takes 10 minutes. And with forward modeling, it takes weeks to get that level of response. And so this lets us use dozens and dozens of these systems to collect data over large areas because the processing requirements have been reduced. Here's some data then from 2008 from the bottom of the Harkin Slough Pond. We put a network of probes. These are actually sample sites. 8 of them were instrumented. And these are profiles. They're color-coded based on location. Let me highlight a couple of issues here. So the blue curves are from this end of the pond, and then these that are with the green area here and sort of the orange and red are from this end of the pond. This is 3 months of data, and this is a log scale. So there's 1 meter per day. That's about 3 meters per day. You can see that at this end of the pond, we had very high infiltration rates initially. In fact, higher than the pond average, which is the data shown here in white. But in fact, after about a month, these rates plummet on the north end of the pond. But curiously, in the south end of the pond, the rate of recharge actually increases continuously throughout the period of recharge. And let me illustrate this in another way that's kind of interesting. Here's going to be one set of data from the middle of January, the middle of February, and then the middle of March. Here's the same data set, but now shown in map view and contoured. And the areas in dark blue are the fastest seepage rate. This is in January. Slower seepage down here at the south end of the pond. A month later, the area fastest seepage is migrating towards the south. And a month after that, it's all the way on the south end of the pond. There's a concept in hydrology called the variable source area concept that's used to describe runoff in basins. And it's the idea that different parts of the basin supply water at different times. It appears that what we're seeing here is a variable recharge area concept, which hasn't been seen before because we've never had data like this before, illustrating how the locations, the timing, and the rate of recharge migrate across a surface like this. We don't know whether this applies to hydrologic basins in general because, again, we don't have data of this kind for larger regions. So this is a way in which the pond functions as kind of a natural laboratory for recharge processes. I'll also note, I'll show you later a plot. We had 8 locations in '08. This year we have 22 locations distributed across the pond, so we're working on mapping this out at higher resolution. Now there's something else we can do with this kind of data that we haven't been able to do before, and that's determine how the hydraulic conductivity at the base of the pond varies with time. And we do this by applying Darcy's law. Darcy's law says that the rate of flow is directly proportionate to the head gradient multiplied by a coefficient of proportionality called the hydraulic conductivity. And we use the thermal probes to get the seepage rate. So this is done independent of Darcy's law. We measure the head gradient using pressure gauges, which are installed in shallow piezometers on the base of the pond, and then we can solve for the hydraulic conductivity. And I'm going to show you some data collected along this set of instruments in 2008. Here's the hydraulic conductivity of the pond on a log scale, and here's the same 3-month period. And what we actually see here is an increase in the hydraulic conductivity of the soil by about an order of magnitude during the first week or two, and then a decrease of about 2 orders of magnitude of hydraulic conductivity of the soil. That lasts for about a month and a half, and then things kind of stabilize. This is pretty permeable. It's a unit known as a Darcy. It's like a medium grain sand or fine sand that's well sorted. But by the time you get down here to 10 millidarcies, the permeability is greatly reduced, and that limits the amount of infiltration that can occur. I'll note that these are all saturated hydraulic conductivities. We are making these measurements in places of the subsurface where there's full soil saturation. If people are curious about the unsaturated case, I can talk about that at the end of the talk during questions. So this is pretty amazing that we can get daily estimates of the hydraulic conductivity and actually map out then spatially and temporally the process of clogging at the base of the pond. So why does this occur? Well, there's a lot of reasons in the literature why people think these ponds tend to clog up, although rarely is it possible to ever determine the exact reason in any particular pond. One of the big issues is the accumulation of fine-grained material. This can be locally derived from the side of the pond, or it can be material that's added along with the water. We've been measuring the suspended sediment load of the diverted water as it goes into the pond, and in fact, those data suggest that that load is quite small. But this is an area developed for agricultural, for the agricultural economy, and the grower who operates a field over here, in fact, discharges some of his irrigation water into the pond during high flow periods, and that seems to be carrying quite a bit of sediment. As I mentioned earlier in the talk, every year the water agency comes in and they scrape the pond out, they pile up the scrapings, and then they bring in wheelbarrows and they remove this material. This shows the pond while it's being scraped. So here's an area where it's been scraped, and here's an area where it hasn't yet been scraped. And I was standing right down there and then took this photograph showing some of that crustal material. We've done hundreds of grain size analyses on samples collected spatially across the pond and at depth over a 3-year period. I'm just going to show you a couple results here. But there's some interesting things. We do see differences in the shallow subsurface spatially in the pond. D10, sometimes thought of as a critical parameter. It's the size fraction for which 10% of the material is finer. And it's a diameter, in this case, of about 100 microns. In the southern part of the pond, the D10 is about 30 microns, about a third of that. So there is a fundamental difference in this significant grain size. The smaller grains tend to have a big impact on hydraulic conductivity or permeability of the soil, and that's because they can clog up pore spaces relatively easily. We also collected samples of the crust from several places around the pond, and it's a completely different population in terms of grain size. And in fact, the peak in the size is between about a half micron and about 4 microns. One of the other things that we did, though, was to go back and repeat sample in the subsurface, and this was a huge surprise. This is a plot of that fine fraction of sediment, the same size fraction that's dominant in the crust, as a depth below the ground surface. These are samples that are hand collected with a soil auger. This was before recharge at 3 different locations, and this is the exact same locations are offset by a few feet after recharge takes place. And what's curious here is, in fact, we saw the exact opposite of what we thought we would see. We thought we'd see a buildup of fine-grained materials in the subsurface. And instead, it appears what happens is, during the early phases of recharge, fine material is being washed down through the shallow sediment column. And in fact, that small fraction is missing after recharge takes place. That may help to explain the short period of increased hydraulic conductivity at the start of the recharge season. Okay, I'm going to shift gears now a little bit and move into the section here that really deals more directly with the CITRIS effort. There's a lot of reasons for enhancing groundwater recharge, and I probably don't need to go through all of these. But one that's really important is that you can combine it with low-impact development strategies, and particularly stormwater capture. It's something that a lot of basins are working on, although what we tend to do is to route water off of the human landscape as quickly as possible. And if we can combine managed recharge with stormwater capture, we can actually take some of that excess surface water and get it into the ground. This is appealing for a wide variety of reasons, not the least of which is that water projects are inherently contentious politically, and there tends to be some agreement on trying to live within your means. And so when basins undertake projects where they try to make maximum use of what's available as opposed to bringing in water from elsewhere, it tends to be more politically viable. Now, there are problems, however, with implementing enhanced use of managed aquifer recharge. And two of them are places where the CITRIS program and our work can particularly make a contribution. And that is that groundwater is cryptic. Unlike the water behind a reservoir, it's not possible to look out into your field and see how much groundwater is present there. We can make measurements, but the ability of projects like these to be implemented are going to be greatly enhanced if people can see the response of the aquifer system in near real time. In addition, the monitoring in real time can help with management, seeing when the system is clogging up, why the recharge rate is decreasing, and then modifying operations in order to enhance recharge to actually take best advantage of the amount of water being put in the ground. So with these ideas in mind, we wrote the seed grant proposal for the CITRIS program and teamed up with a group in the electrical and computer engineering program. And here's what we did. We picked out an area in the pond, and this was in the 2008-09 water year, so after the data were collected that I just showed you, and put together what we call the RATS system, Remote Autonomous Temperature Sensor Network. And the idea of the RATS network is to provide this information in real time, because right now all of our thermal data are being collected by autonomous loggers. You have to wait 8 months, go out into the pond, pull the loggers out, and then download them. With the RATS system, the idea was to bring the data back to our desktops every minute so that we could actually see what's going on as it's occurring. We have a base station set up on the edge of the pond. The data get transferred there from a series of nodes. Then they get up. They could either be downloaded manually by driving out in the field in our field truck and downloading the data, or they could go back to Santa Cruz with an Airlink modem. And then we have a virtual PC set up there through the School of Engineering and a website, which sadly today is down. I was hoping I was going to get to show it to you, but because it's a virtual machine operated through the School of Engineering, whenever we have a problem, we just go into the queue. This is one of the issues with having a virtual machine instead of our own machine. But most of the work has gone into the physical sensors themselves and establishing the network. And these were built completely from the ground up by a student team. And the concept was to put together probes. This is about a 1 meter probe, and it's made, the outside casing is made of PVC. There's a computer board that was designed by the students and then implemented with the help of our researcher and faculty team. And in the latest version of the probe, it actually lives inside here. In an earlier generation, it lived in a housing on the top with which we had some problems. We bought high-resolution thermistor sensors, and these are built into these buttons, epoxied onto the surface, so they have a very, very fast response time. The response time the time constant for these is less than 5 seconds, where for the autonomous commercial loggers, the time constant is about 2 to 3 minutes. So you get much higher resolution data with these. And then this is installed, as I said, inside the head of the node, and the data then is wired back to the local base station for telemetry. So here's Eric Castillo and one of our undergrad helpers putting a hole out here in the base of the pond. You can see some of the other instruments back here that were already installed. And then here's the probe system being lowered down. You can sort of see the wire coming off here back to the base station. We backfill the holes with silica slurry to assure good thermal contact with the formation. This is another potential advantage over the autonomous systems that we use, which are inside PVC pipes filled with water. That increases the time constant to on the order of 5 to 6 minutes. Okay, so these should have a much stronger response time. Here's what one looks like when it's fully installed. That's the leftover silica slurry. And here in the field, as of last fall, are 4 of these deployed, and then a whole variety of other instruments that we put in. These are tubes through which water samples are collected off to the side of the pond. So we deployed the RATS network adjacent to the other instruments so we could do a side-by-side comparison of the results. And here's what the network looks like as it sits now. We actually have monitoring overall at 22 locations, so many more than we'd had in previous years. The RATS network is associated with this part of the pond, and I'm not going to have time to go into it, but we have a trench bypass system that we're also attesting here to try to get more water into the ground more quickly. And the RATS instruments are associated with those trenches. Here's some of the first data to come back. This is a record from the current year. We went out and downloaded the data right at the end of April and then processed it using the same methods that I showed you earlier. The pink curve is from here next to one of the trenches, and the blue curve is from here. We're definitely seeing the effect of more rapid recharge here. Not clear if that's directly associated at this point with the trench or not. We have autonomous instruments, separate instruments deployed in the trench. We'll have to recover those in August in order to find out how these two are going to compare. In fact, there were two other nodes of the RAT system here, and here's their data plotted up. They look more like this sensor, so it does appear, they look more like this sensor, so it does appear that this one here is somewhat anomalous in flowing at a somewhat lower rate. The rates we're getting are comparable to what we saw from our thermal sensors in previous years, but we're going to have to see when we pull out our autonomous thermal sensors this year how well the rates compare. Again, we have to wait because most of our sensors aren't hardwired in, allowing us to get telemetry. Most of them are sitting there all by themselves. So what remains to be done in our CITRIS project is we're collecting data today. The network is pulling the probes every minute. That's 15 times the resolution we're getting with our autonomous sensors. We're going to recover the RAT system and see how well it held up in terms of the mechanical components. It appears to be working fine. In previous years, we had flooding of some of the nodes, and that was a problem that we were able to fix this year. We also want to evaluate how the different sensor systems compare. We're collecting sediment samples at the sites of the RAT sensors so we can evaluate how the flow rate varies with sediment accumulation over time. Probably the biggest thing we need to do is work on the digital signal processing techniques so that we can do the analysis outside the frequency domain. Because right now there are strong edge effects in the filtering that takes place. This is standard, as most of you guys know, with digital signal processing. But because of that, you need to have 3 or 4 days of data beyond the time of interest in order to avoid the edge effects. And the filtering is absolutely essential in order to remove frequencies other than those that we want to examine. But we need to figure out a better way to extract that signal more quickly, which will get us into the realm of real-time monitoring. We picked thermal sensors because of the ability to do the seepage analysis. But in fact, it would be nice to wire in additional sensors, pressure, and water quality sensors. We could have salinity, nutrient content, and so forth to provide that information in real time. Right now, the web interface is quite crude. We're just sending back digital counts and then doing the processing, automatically doing the processing on the server, and then we get numbers posted to the screen. But it would be nice to have a heads-up display with the actual thermal data. So that needs to be done. Hopefully we'll get that wrapped up this summer. Okay, so how does this all fit into the bigger picture? Well, the Pajaro Valley needs to find lots of sources of new water. There's not going to be one silver bullet. There's not going to be one pipeline from the Central Valley Project that's going to bring in all the water that they need. This is a slide I'd put together about a year ago, but one of the things, before we'd gotten the RATS data back, but one of the things I'd included on here was having distributed recharge systems throughout the basin, especially those near areas of elevated topography that could capture high-quality stormwater runoff. And in addition to having systems near the coastal areas. The ones in the coastal areas are needed in order to try to counteract the effect of seawater intrusion. But the ones are really critical in the back of the basin, both because water levels have been lowered, but also because people in the back of the basin right now don't get a sense that they benefit from water projects that serve the front of the basin. And it's all one basin politically, and I think to get the players on board, everybody needs to have a chance to see some benefit. In addition, we have some ideas and are talking with stakeholders in the basin about setting up a program that looks something like this. We find a series of areas that drain on the order of 100 acres, set aside a small amount of area to have a combination of a groundwater recharge pond and a constructed wetland, which can help with a little pretreatment of the water, lower the sediment load, lower the nutrient load, route that water through the constructed wetland into a smaller MAR pond like the Harkin Slough Pond. There would need to be an offset for the growers who set aside land for this purpose, but we're talking with one of the major buyers in the basin about setting up a program for this. And in fact, there are state and federal programs for exactly this kind of payment. In addition, we're talking to the Water Agency about having a reduction in the groundwater augmentation fees that the growers pay in order to allow them to get some benefit. It's essentially like running your power meter backwards by having a solar panel on your roof. Without that incentive, people don't have much of an incentive to contribute to the greater good. So this has not been set up yet, but it's in the works, and I'm confident that we can come to some kind of an agreement. Then we need the instrumentation. The CITRIS data is critical because the growers who are allocating the land and who are facing the inconvenience and at least a modest economic hit for participating in the project need to be able to see the effect that their projects are having. And having that instrumentation available with real-time water levels, water quality, and infiltration rates is going to go a long way towards creating engagement within the basin, letting stakeholders feel like they're actually a part of the solution and contributing to a solution to the water shortage. So this will provide both a technical benefit and a public engagement benefit for systems of this kind, which need to be distributed across the basin in order to avoid the high cost of the infrastructure needed for projects like the Harkin Slough project. So this is the key area, I think, where the CITRIS-related work is going to play a role. So there's a lot of challenges to addressing the need for freshwater resources in the Papua Valley. Negotiations are ongoing, and these are going to need to continue in the next couple of years. We need to find an appropriate supply. Stormwater runoff looks like a good bet. There is recycled water being used in the basin. So far, it's not being used for groundwater recharge, but some of it probably could. We need to locate the best areas to put that water into the ground. Again, as I suggested, some of those are going to be in the back of the basin, and it is going to take a long time in order to bring the basin back into hydrologic balance. And that's the reason why there needs to be public engagement. If it's going to take 10 or 20 years till we start to see the water levels come up, people need to see the water going in now. We can't tell people that they've got to make a contribution and not see the result for 30 years. And using environmental networks is one way that people can see the result, look out their window and see the structures, and then look on their computer and see the water going into the ground. And I think that's going to be critical both for the management of the systems, but also for keeping stakeholders on board, especially those that are skeptical about water projects. If we can't do something like this, the basin is going to have a real problem, particularly if they go into adjudication. This is where the courts take over and a water master is assigned, and then nobody has control in the basin anymore about how their water is allocated. So accountability is critical to avoid that, and that's where the environmental network fits in. So in summary, groundwater is a big part of the freshwater portfolio in California. It has been. It's going to be even more so in the future. But overdraft is a chronic problem all over the state. It's not just a problem for us in Santa Cruz County, but for all of California. And one of the best ways to address groundwater overdraft is through managed recharge. It's a way to make use of the storage that we already have in the ground, but this requires a better technical understanding of recharge processes and groundwater mechanics, arguably one of the hardest parts of the hydrologic cycle to understand. In the Pajaro Valley in particular, the Harkin Slough project can infiltrate at rates up to about 5 meters a day. It's the equivalent of about 15 acre-feet of water per day. For the Pajaro area, it's a relatively large pond. There are many larger systems around the state of California, but in a small basin like this, it's a pretty large structure. We can use thermal methods in order to map out the rates, the timing, and the distribution of infiltration and groundwater recharge. And then we can network these thermal probes in order to provide that information to us in real time so water managers and stakeholders can understand how their systems are working. There are options for enhancing recharge in this area, but it's going to require some creativity in the application of existing and developing technology to pull off large-scale projects like this one. And with that, I thank you, and I'm happy to answer any questions you have.
So we have time for a question here.
Hi there. So I have some questions about what large-scale implementation of those recharge basins in the back basin might look like in terms of overall adjustments to the peak flows. And particularly, what would that mean? I don't know if this watershed bears salmon, but adjusting the peak flows and the effect on fisheries.
Sure, it's a great question. And in fact, let me go back to that figure. So there is an anadromous fish habitat, which is Corralitos Creek. It's a big steelhead. They have a steelhead run. These areas don't drain into Corralitos Creek. That watershed clearly needs to be protected. But we've done work in Corralitos Creek measuring flow and loss, and I can tell you that system flows at relatively high flows for about 3 to 4, 5 months a year. And the rest of the time, we've seen fish this big in pools that big, isolated from the rest of the river. Another part of this overall system this is my fantasy for the future of the Pajaro Valley, is actually taking excess flows which are released upstream from San Benito and Santa Clara County from their water treatment plants and getting that water up into Corralitos Creek to keep it running. But in addition, there's loss along this area in green. Corralitos Creek recharges the aquifer. These are not in the Corralitos Creek watershed for exactly that reason. In the case of the Pajaro River, the vast majority of those winter flows just go right out to the ocean. And sadly, there's not much by way of fish here in the Pajaro River. There's some, but the main run is up on Corralitos Creek, which is a more pristine watershed. But the idea here is to catch these peak flows. And in the winter, the Pajaro River flows at 10,000, 15,000 CFS, and capturing a few hundred CFS here is not going to have a significant impact on the riparian habitat. These would be operating during the winter storm periods. And that's exactly the time when we're not worried. In fact, there's flood control projects along the Pajaro River, that operate during those periods. So I think this is one of, 20 years ago, people didn't look as hard at projects that would supply water for 3 months a year. It was thought that wasn't very efficient. And I think what's changing now with the value of water and recognition of how serious the problem is that we can consider projects that really run for 3 or 4 months a year as being potentially beneficial and worth implementing. So they're good points, but I think we can address them by careful implementation. Yes, please.
Sorry. I can imagine drawing a directed graph where we have sort of a chunk of land and an arrow pointing, say, upstream, and we would get a network against which the water was flowing. And if you took the connected component from the entry into the ocean, you would get a watershed if you went out. So that gives you a watershed connectivity graph. And I suppose it's probably kind of fractal or something, like you were pointing out this one flows down, but those two don't flow to each other, et cetera. And it seems that conveniently, in this case, you're saying it's all one political local zone. Maybe it's a county or something.
So the Pajaro Valley Water Management Agency is a special act district, and they actually have parts of 3 counties. They have overlapping jurisdiction.
So someone had the wisdom to create such a political entity that mapped to the water locality, the political locality to the water locality. So that's what I'm... what I'm interested in is throughout I don't know if you know this, but throughout the United States, how often is it a problem where one watershed, where watershed locality does not embed into political locality, thereby causing problems? And is that really still a problem? And it seems like maybe here it isn't. And if so, do people recognize that as a problem?
Yeah, so here's the, So here's the, I think you might have come in after we got past this slide. Yeah, no worries. So this is the watershed for the Pajaro River. And it's quite a large area. It actually encompasses 4 counties. Here is the Pajaro Valley groundwater basin. And it overlaps with that, but it's got this part of Monterey County, which is not actually part of the river watershed, strictly speaking. So yeah, in this case, this district was created in '84 by the California legislature in recognition of the overdraft problem. So they were essentially charged with managing the basin more effectively to eliminate the overdraft. And in a way, that's what gives me some hope. Although, of course, if you talk to growers in the back of the basin, they argue that the seawater intrusion in the front of the basin is not their fault. So even though they are politically one basin, there is debate among stakeholders as to who's actually responsible. And I think we take advantage, exactly as you're saying, of the fact that it really is one basin. And in fact, the transmissivity of this aquifer is huge. And you can see in groundwater models that have been done of this area how the back of the basin and the front of the basin respond to each other, to different scenarios of pumping and so forth. But trying to use that as motivation for people in the back of the basin to support projects that are put in the front of the basin is probably a tough It's a tough battle. I think that's why one of the solutions is to distribute the projects all over the basin. The fact is that water levels are down in the back of the basin. It's just they don't have the ocean right here to get drawn in. So people in the back of the basin, if they can see some benefit, and particularly if they can make their water meter run backwards by implementing projects, they'll be helping everybody. And in that way, they can become engaged in part of the solution instead of simply feeling like they're being taxed for the solution, but they're not actually getting any benefit from it.
Sure. Do you know throughout the United States how often it is that the water basin locality does not have the political locality well?
Yeah, so how often is this done? I don't know offhand. I mean, California is a funny case because we're the last Western state with no statutory groundwater management. And so all we have are the individual basins in California that have been, like this is a special act district. It was created specifically for this purpose. Other special act districts don't obey hydrologic boundaries. And this one is even more than most because of the backstop of the San Andreas Fault here. I mean, it's really thought that no water crosses that divide. So this is a water district managing an area that's pretty well contained hydrologically. The big exceptions are along these edges, and there is water that moves probably in from the north here, and it's not quite clear what goes on here to the south. So it's not 100% coinciding with the hydrologic boundaries, but it's close. It's pretty close. And my guess is this is an anomaly. It certainly is in California, and I don't know about the rest of the U.S., but I would guess it is an anomaly.
Okay, well, I think we're short on time, so I think we're going to end right now. And if you have any questions, you can join them afterwards. So thank you so much, Dr. Fisher.
Sure. Thank you very much.